Georgie sir has told, it is a privilege to talk about dialysis circuits on the Teachers' Day. Thank you, sir, for this opportunity. Anyway, I'll be talking about hemodialysis circuits. Yeah, the slide is not moving right. So. Okay, let me start the topic. We know that hemodialysis is a process where the machine pumps the patient's blood against a dialysate that is generated by the dialysis machine. That is what all of us do day in and day out. And to study this, we have two circuits. We all know there is a blood circuit and a dialysate circuit. So the dialysis machine basically pumps blood from the sucks blood from the patient's blood vessel and pumps it to the interface where it comes into contact with the dialysate and does the dialysis and ultrafiltration and returns it back. So the knowledge of the components of the circuit, both the blood circuit as well as the dialysate circuit, are important for patient safety and care. And all the DPs should know the basics of the dialysis circuit, blood circuit as well as the dialysate circuit. So this is our machine. We are daily working on it. It has got three parts. One is the head part of it, that is where you communicate with the machine. You have the monitors and operator inputs, treatment parameters, and receives information. And the second part is the extracorporeal blood module, blood circulation module. This is the main part we usually manage. And the next part is the lower part of the hydraulic system, of which all of us frankly doesn't have much idea, and we depend on others for any problems in this part. That is the preparation of the dialysis fluid and delivery. So the blood circuit, we all know that there's a tubing, tubing has a provision for anticoagulation, pressure monitoring, as well as air traps. We have a blood pump and a dialyzer. So all of us are familiar with this. We don't need to waste time on this. The blood is being sucked in. Sorry. Blood is being sucked and it goes through an arterial pressure monitor, which we rarely use. Then it goes to through the blood sucking pump, and then here we have the heparin pump for anticoagulation. Again, another monitor here to measure the pre-dialyzer pressure, which we usually don't do. And then this is the dialyzer and comes back through the venous chamber, venous air trap, and then returns back to the. So that is very clear and doesn't need any explanation. Now, this is one pressure profile of the dialysis circuit. Is one thing that all of us, the DPs, might not be familiar with. I'll just take a few seconds in this. We know this is the blood circuit can be divided into an arterial circuit, arterial side, and a venous side. The side prior to the dialysis is called the arterial limb of the circuit, and after the dialyzer, the segment that is coming is called the venous segment. And we know there are two tubings. The arterial tubing is one, and the venous tubing is other. So this is arterial needle, and this pump actually we know the blood pump is a rotor pump which squeezes blood by compressing this pump segment of the tube, and so that it creates a negative pressure and sucks blood through it. So the first segment of the arterial limb before the pump is a negative pressure segment, and if you measure the pressure here, it will be negative. So that is important because a negative pressure sucks air from the atmosphere, and if you have an air embolism or any problems like that, you are suspecting, you have to check the access and any leaks somewhere here that is causing air suck. And when we go to the next, after the pump, obviously the pump is pushing pressure inside to the tubing. So there will be a high pressure system. As we all know that in the high pressure system, the apparent pump, if you don't go pressure the apparent pump, the blood will accumulate in the apparent syringe. We know that. And then goes to the dialyzer. Dialyzer is the interface between the two circuits, the blood here and the dialysate here. And we know the diffusion and ultrafiltration takes place here. And then it comes out, coming to the venous limb, the pressure again, it's a low pressure system. This is a high pressure system in the post pump or a pre-dialyzer arterial limb, but the venous limb is a lower pressure system. So this is a profile like in the arterial limb. Before the pump, it is a negative pressure. After the pump, it is a positive pressure. And then in the venous limb, it is coming down. The venous pressure is coming down, but still positive. So that much about the blood circuit. Blood circuit as such is a big topic and needs a special separate discussion. I would try to concentrate on the dialysis circuit because that is a black area among the DPs as well as the nephrologists. So we know there is a water source and from the raw water that is coming, we subject it to a water treatment plant. And obviously we know the water treatment plant, the components of it. Then after that, the treated water goes to a heater, and the heated water, the treated and the heated water goes to an aerator where the air is deaerator, where the air is removed, and then it comes to the proportionating system or the proportionating chamber, where we nowadays use the bicarbonate solution with this bicarbonate dialysis, not the acetate dialysis. If it is acetate, there's a single concentrate, but in a bicarbonate system, we have a acid and a bicarbonate A and B that is mixed with this treated and heated water in a specific proportion to form the final dialysate. And it goes through like a security check. It goes through the checking for the pH, the conductivity, and the temperature. And once it is found safe, it is delivered to the dialyzer. If it is safe, if it is not safe, then it bypasses the dialyzer and goes to the drain. One more thing is the ultrafiltration occurs by a volumetric control system, which we'll come to subsequently. So this is the RO plant, the water treatment unit, which is there in all our dialysis units, and the DPs should be very familiar with all the components of the water treatment unit. We know the raw water is stored, and then it comes through the sand filter or the pre-filter, then it goes to the multimedia, the water softener, and then goes to the charcoal filter, and then we have pre-filter here, or the 5 micron filter, and then goes to the RO plant or the RO membrane, and then the RO water is collected in the storage tank and pumped through a closed circuit that should be continuously circulating. All of us know about this, so we'll quickly go to the next. So what is the importance of this water treatment? So one thing is we should know that a person, we might drink 2 or 3 liters of water per day, and our gastrointestinal tract is the membrane that protects it. But the water for dialysis, in a session of dialysis, around 120 to 200 liters of water is being exposed against a membrane, and that should have a quality much superior to what to the potable water we drink. So there is a minimum standard of purity for water. That's the AMI, the Association for the Advancement of Medical Instrumentation, that gives the chemical standards as well as the bacterial standards are important. We measure as the colony forming units and the endotoxin levels. So the AMI, just to mention, has measures various metals and non-metals, and that is the maximum allowable concentration of aluminum, chromates, chloramines, copper, fluoride, nitrate, and I think all the units should at least have a basic record of these metals in your unit. And what is the importance of this? We know there are clinical emergencies that can arise due to water contamination, like copper or cuprophene that is released from the heating element or dialyzer may cause severe hemolysis. Chloramines and nitrates that come from the water can cause severe hemolysis. Fluoride can cause pruritus, nausea, and ventricular tachycardia, at times fatal ventricular fibrillation. Aluminum, we all know that it can cause bone disease, anemia, fatal progressive neurological deterioration known as dialysis encephalopathy syndrome. Again, lead, copper, zinc, and aluminum can leach from the metal pipes. We don't usually use metal pipes because of this problem. We use the PVC pipes nowadays and cause anemia. So coming to the dialysis circuit, the key components of the dialysate circuit include heating, deaeration, proportioning, monitoring, ultrafiltration, and disinfection. We'll go through all these components quickly. So first, the treated water from the RO plant is subjected to heating. Heating the treated water assists in degassing the cold water, but that means that the cold water contains some air in it, and to remove that air, you can heat it so that the air bubbles out. And water is heated to the body temperature so that it is compatible with the blood. And this is heated by stainless steel heating elements. And temperature monitors I have shown earlier is there downstream in the machine. So water is heated to physiological temperature once the heated water is subjected to a negative pressure, it will remove the air. I'll show you in this diagram. So the heated water is coming like this, and this pump gives a negative pressure here, so that in this air trap, the air is being removed and it is pushed out through the air vent, and the blood is pumped out. Deaerated blood is pumped out to the next segment of the dialysate. The next segment is the proportioning segment of the dialysate circuit. It's proper mixing of heated and treated water to produce the appropriate dialysis solution. I mentioned earlier about the solution A and B, and the solution A contains acid, chloride salts, including sodium, potassium, calcium, magnesium, and acetate. And bicarbonate solution, we know that we have the powder that we have to mix it and subject to them in a can and subject to the machine, or we have the buyback system now where the dry powder can directly be attached to the machine. So you can't make a prepared bicarbonate and keep, because it releases carbon dioxide that can encourage bacterial growth. So this proportionation occurs in the mixing chamber, and one important thing is that there are many companies that are producing this concentrate. As far as the acid concentrate is concerned, when you are changing a brand of an acid concentrate, we were purchasing from a person A. Now we are going to purchase from person B. So the composition might change. So accordingly, we have to change the settings of the machine so that the proportionation will be proper. You can have either a 34:1 or a 44:1 concentration for an acid. But bicarb, usually we mix in a ratio of 20:1. And this mixing is usually by a diaphragm or a piston pump. And the final dialysate will have the concentration like this. Sodium, almost same as what we have in a blood, 134 to 145. Potassium, we know that we have K0, K2. Calcium also, we have a standard 2.25. But again, if you can have a low calcium bath that is custom made, magnesium chloride, bicarbonate, and sugars. These are the ranges. And when we come to the dialysate monitoring, I told the pH should be physiological pH of the dialysate should range from 6.8 to 7.6. Again, the temperature. I was mentioning about the temperature monitoring downstream. Here comes the temperature monitor. So the temperature should be also in the physiological range 35 to 42 degrees Celsius. Low temperature causes shivering, and high temperatures causes protein denaturation or hemolysis. Now, what is conductivity? We daily hear about conductivity, high conductivity, low conductivity. It is simple. Conductivity is the amount of electric current conducted through a dialysate, and it reflects the electrolyte concentration of the prepared final dialysate. It is basically to check whether the electrolytes concentration of the dialysate is perfect and suitable for treatment. The principle is a constant voltage is applied across two electrodes that are placed 1 centimeter apart in the dialysate flow line. If the concentration of the electrolytes changes, the voltage changes and the conductivity changes. So what's the normal conductivity? It should be between 12 and 16 millisiemens per centimeter. Usually we keep it as 14. The greater the number of fines, the greater the conductivity of the dialysate. And you should know that it is affected by temperature and concentration of the acid to base composition. So once the conductivity alarm sets in, the dialysate stop flow if it comes out of the limit. So I told earlier that it goes to the bypass circuit. So this is the electrodes in the dialysate passes through the cell, and if the composition is different than the alarm rings, and what happens, like you can see here, this is the normal range of conductivity. So that normal range of the dialysate will be isotonic, and the blood cell RBC is shown here will maintain its normal shape. But if the conductivity is high, that means the dialysate solution is hypertonic. That is, the blood is subjected to a hypertonic solution. What happens is, in the hypertonic solution, the RBCs will shrink, desiccate, as you can see here, and the other way around, if the conductivity is low, what happens is a hypertonic solution, so that it will swell up and burst, causing hemolysis type of thing. So conductivity is very important, and the monitoring of conductivity as well as alarms. So when does the conductivity alarm occurs? Empty concentrate jar, that's most common. The machine rings the alarm, and automatically it goes to the bypass circuit, but the pump goes on running. And if you don't see that the pump running, means the dialysis time, the clock of the dialysis will run on, but effective dialysis doesn't happen. Empty concentrate jar is one thing that all of us, it's like a knee-jerk reflex. You get an alarm, you see that whether the concentrate is empty or not. Changes in the electrolyte concentration of the dialysate, abnormal inlet water pressure, and water leaks and puddles in the mixing chamber, and concentration line connector is unplugged. These are the problems. I was talking about the bypass pump. The bypass circuit. Bypass valve means that the final dialysate that is coming, before going to the dialyzer, there's a clamp here. If there is some abnormal signal happening upstream, this clamp closes and it bypasses. So in a 4 hours dialysis period, if 30 minutes goes bypassing, then net dialysis that the patient gets will only be 3.5 hours. And now this is a dialysate pressure monitoring. This is important because the dialysate pressure, that is the pressure of the dialysate component of the inside the dialyzer, it can range from -400 to +350. That's a wide range with the accuracy of plus or minus 10%. So the pressure in the dialysate compartment should not exceed the blood compartment in the dialyzer, because then a reverse thing will happen. Like if the pressure in the dialysate compartment is high, the membrane will rupture, and the unsterile dialysate may contaminate the blood, and that can be catastrophic. And the rupture of the membrane can occur. And the ultrafiltration is an important component that is determined by the pressure of the dialysate. Ultrafiltration is controlled by what is called the transmembrane pressure. We'll come to the details of transmembrane pressure, or TMP. Basically, let me just define it as the TMP is equal to the pressure of the blood outlet minus the pressure of the dialysate outlet in the dialyzer. So two things, TMP, we are concentrating on the ultrafiltration. TMP is the difference of the hydraulic pressure and the fluid, hydraulic pressure in the blood and the fluid inside the dialyzer. And what is the KUF? KUF means the ultrafiltration coefficient, otherwise called the leakiness of the membrane. It is defined as the ml of blood transferred across the membrane per hour when the membrane is subjected to 1 millimeters TMB. So that is the leakiness of the membrane, and means otherwise called the flux of the membrane. When the KUF is increased, we say it's a high flux membrane. It gives efficient ultrafiltration. So this is a cartoon which shows the transmembrane pressure. This is the blood out of the dialyzer. This is the dialyzer, and this is the starting of the venous limb of the circuit. Now you can see the pressure here is plus 100, and this is the dialysate component, the dialysate out. That is the spent dialysate is coming out. The pressure here is minus 50. So TMB is the sum of these two. Although we say the difference, the effective TMB is adding these two. That is minus 100 or plus 100 minus 50. When you add that, you get a plus 50. That is the transmembrane pressure that is subjected here, and you have a pressure of plus 50 that is pushing fluid from the blood compartment into the dialysate compartment. So we'll just see a equation like that we have set a ultrafiltration goal of 4 liters to be removed, and over a period of 4 hours, and we are using a dialyzer with a KUF of 20 millimeters. That means 20 ml of fluid is removed from the blood using this dialyzer when you are keeping 1 TMB, 1 millimeter TMB. And so the ultrafiltration rate, that is, you have to remove 4 liters in 4 hours. In an hour, you have to remove 1 liter. So the TMB is calculated by the machine, like the ultrafiltration rate by KUF. That is, for this 4 liters to be removed with the dialyzer of a KUF of 20, requires a TMB of 50 millimeters. So I think I'm clear, and you don't have to do anything. You have to just, the machines are so sophisticated, you have to just type in the UF to be subject, UF to be removed, as well as the treatment time. The machine automatically gives the TMP and subjects the circuit to the TMP. So this is important because when you're using high flux dialyzers and removing large amount of fluid, especially when you're doing convection-based hemofiltration therapies, you need very accurate control of the ultrafiltration volumes. So for that, you need to have a volumetric-based system of controlling the ultrafiltration. So most dialysis machines have volumetric-based control, which uses balancing chambers. There are 2 balancing chambers that is separated by a membrane, a flexible membrane, and this balancing chambers will continuously deliver fresh dialysate to the dialyzer on one side, and the spent dialysate with the extra ultrafiltrate is flushed out through the other side into the drain. So we'll see how it happens. I'll try to explain it. See, this is the balancing chamber. The fresh dialysate from the RO plant, it's not from the RO plant, the fresh dialysate from the machine after proportionation and all, after checking all the standards, it comes like this. So it is coming here, this valve is open, and so it is entering into the balancing chamber. This white is the fresh dialysate and dark is the used dialysate. This is being pumped. You have a pump here that is pumped into this chamber, and so, and you can see here in the outlet, the spent dialysate valve is open. So you're pumping the fresh dialysate from here, and there's a flexible membrane, and the valve is open so that the spent dialysate is pushed out to the drain. Simultaneously, what happens is the used or spent dialysate is coming out, and you have a pump here that is pumping this valve is open, the spent dialysate to the chamber, and this chamber already was filled with the used dialysate, so means fresh dialysate. So what happens when the used dialysate comes and fills up this chamber, the flexible membrane pushes the fresh dialysate to the dialyzer. So it is a continuous process of subjecting fresh dialysate as well as the used dialysate to the dialyzer as well as to the drain. And one important part is the UF pump. UF pump is a pump that creates the TMB here according to the set levels of the ultrafiltration goal. And UF pump creates a negative pressure here so that the required ultrafiltration is also removed. So that's what I told the UF pump. Now UF pumps are piston type and placed in the used dialysate flow path by negative pressure, I told you. And when the UF pump is off, that means you don't need any ultrafiltration. There is no pressure gradient, that means TMP is 0 between the blood and dialysate line, and no fluid is removed from the patient. I hope it's clear. Now, that was a volumetric control of ultrafiltration. Now, machines have also flow control of ultrafiltration using flow sensors in the outlet and the inlet and outlet of the dialyzer. And you don't need the balancing chamber. You can, the flow sensors can set the what you call TMP and do the ultrafiltration. Now, blood leak monitor is the last component of the dialysate circuit. So the dialysate circuit ideally doesn't contain any blood because the membrane is intact. And if the membrane ruptures, the blood comes into the circuit. That means you have to stop the treatment and change the dialyzer. So how does the machine detect blood? Leakage of blood into the dialysate circuit is detected by blood leak monitor, which is should be situated downstream from the dialyzer. It uses the principle of infrared or photoelectric cell to detect decrease in light from the source. So when you have these red cell particles in the dialysate, the spent dialysate, it will scatter the light and trigger alarm and deactivates it. Automatically the blood pump will stop. So that's a cartoon which shows it. That's a dialysate that is going, the spent dialysate, and if there is blood, this will be activated and it gives alarm and the pump automatically. So even a small amount like 0.25 ml per liter of dialysate of blood will be detected by the system. The chemical purity as well as the microbiological purity, as I've told you, CFU and endotoxin levels are very important for the dialysate. The machine should be periodically disinfected. We have many disinfectants like formalin, hypochlorite, peracetic acid, renalin, etc. So machine should be rinsed between chemicals. You put one chemical, rinse it, then put another chemical. And also before a session of dialysis, you have to rinse the machine before treating session, before taking a patient. Now what we do, we have the citosterol is compatible this thing for a Fresenius machine which we use here. Citosterol is the chemical we use for machine disinfection, and it is a chemothermal disinfectant. That means it has got both heat as well as chemical disinfection, and this works only at a higher temperature, like the machine has to heat it to 84 degrees for this citosterol to act. While when you see the renalin, it's a cold disinfectant. So apart from disinfection, this citosterol also decalcifies the circuit, the dialysate circuit. So that's also useful to clean the dialysate circuit. Any blood somewhere will also be washed away by the citosterol. Now finally, we have a diasafe filter that is being attached to the fresh dialysate before entering into the circuit, into the dialyzer. This is ultrafiltration of fresh dialysate by diasafe plus. And especially when performing high flux dialysis, the risk of endotoxin transfer can be minimized by using the diasafe plus filter, and that is an essential thing for safe dialysis. So let me conclude by telling that dialysis circuit requires monitoring to ensure patient safety. Water safety and knowledge of dialysate circuit should be clear to all the DPs caring for dialysis patients, and also for the nephrologists, they should know their mission in order to safely troubleshoot the problem. So with that, I finished the topic. I think it was useful. I have not bombarded you with much of information, and thank you for the patient listening. I can take questions again.